Hi, everybody. My name is Lorenzo Sorbo. I am at the University of Massachusetts Amherst. And first, I would like to thank the organizers for allowing me to share this presentation. Today, I'm going to talk about axion inflation and how this can lead to many parity-violating signatures in our universe. So let me start from very general statements about our universe. Universe is old, is very large by all standards. In first approximation, it's homogeneous isotropic, and we know that its spatial sections are flat at the percent level. Structure grew out of small scale invariant perturbations. The structure is the galaxies or clusters of galaxies we live in. And the spectrum of primordial perturbations was Gaussian to a very high degree. Let's say at least a part in 10 to 3 or so. It's quite remarkable that all these important facts can be explained by the simple assumption that the universe underwent a primordial period of inflation. What's inflation? Is a time of accelerated expansion of the universe when the universe is filled by a scalar field with a potential that is sufficiently flat. Now there's a problem when we go to model building, that is, if I write down a Lagrangian that involves a scalar potential that is sufficiently flat, in general, loop corrections will spoil the flatness of this potential in a potentially unpredictable way. So how can we make sure the radiative effects don't change my classical potential a lot and are under control? And there's a way that, of course, is based on invoking symmetries. Symmetries are always good to keep things under control. In particular, what we are interested in is what is called the shift symmetry. A field phi has a shift symmetry if the theory that describes it is invariant under transformation phi goes to phi plus a constant. Of course, if the symmetry is exact, then there is no potential possible for phi other than a constant, which is a cosmological constant. Cosmological constant is a great mechanism of inflation, but it has the real problem that inflation never ends. So it's really an overkill. But one can break the symmetry a little bit and generate a potential using typically degrees of freedom that are known as pseudo-Nabu-Goldstone bosons, PNGBs, that have the property of being, besides being approximately shift symmetric, they're also pseudoscalar, which would be important for us. So in these two slides, I hope I convinced you that there is some reason to believe that the early universe could have been filled by some pseudoscalar that is parity odd. And of course, if the universe is full of something parity odd, you might wonder whether this violation of parity shows up somewhere. In particular, I will be focusing on this coupling of our pseudoscalar inflaton to U1 gauge fields. This coupling respects all the symmetries I've been mentioning. F alpha is a coefficient of order 1. F is a constant with the dimension of an energy. If one quantizes the gauge field on the top of this rolling inflaton, one gets equations of motion for the mode function of the gauge fields that read this way. Why is this interesting? It's interesting because this parameter lambda here is either +1 or -1. And this means that, let's say, for phi prime positive, phi prime being the conformal time derivative of the inflaton, if phi prime is positive and lambda is negative, this quantity can be negative. So this means that one of the two helicity of the photons can have effectively a tachyonic mass term, which means it will be exponentially amplified. Actually, one can sit down and assuming that phi dot derivative of the inflaton with respect to the cosmic time is constant and h is constant, one can compute the amplitude of, let's say, the left-handed photon to be exponentially amplified, and this one obtains this result, while the right-handed photon is not amplified at all. So now we have, therefore, a situation where our early universe is full of a large population of chiral vector fields. The chirality of the vector fields is this reflecting the parity-violating nature of our background. And these chiral vector fields in the early universe can lead to a lot of effects, and so there's a potential for a very, very rich phenomenology, which has been studied in all these aspects here over the last 15 years or so. In particular, what I marked in red are phenomenological effects that are strictly related to the parity-violating nature of the system, and I will focus mostly on these two in boldface, parity violation in CMB, and in particular parity violating gravitational waves at interferometers. So why gravitational waves? Well, when the early universe is full of these photons, that by the way might be standard model photons or some other U1 gauge fields, you can have a phenomenon where two quanta of these vectors join to form a gravitational wave. And since these vectors are left-handed, the gravitational waves will be preferentially left-handed. So we have a mechanism for producing chiral gravitational waves. What's the spectrum of these gravitational waves? It's computed in some approximation in this form. So this is the power spectrum of left-handed gravitational waves and power spectrum of right-handed gravitational waves in this scenario. This contains two components. The standard one, you have a one here and the one here. This is parity invariant, meaning the left-handed and right-handed gravitational waves have the same amplitude. This is just the standard spectrum of gravitational waves produced during inflation. This part here, proportional depending on this parameter psi, on the other hand, is induced by the presence of the photons. One can see that it's parity violating by the fact that these two coefficients are different. So left-handed are larger than right-handed. The parameter psi is given by this expression, and these formula are valid in the regime in which psi is larger than 1 or 2 or so. In general, psi will not be very large, so think of psi to be a parameter of the order from 2 to 5, 6, 7. So this can lead to some very interesting phenomenology. Now we have primordial gravitational wave during inflation with this exponentially large amplitude and parity violating. Unfortunately, there's a problem. The same mechanism that leads to production of gravitational waves will also lead to the production of scalar fluctuations. And the photons are produced by the amplification of vacuum fluctuations, so they have naturally satisfy a Gaussian statistics, but now this is a two Gaussians producing one particle process, and so these guys here are not Gaussian, very badly not Gaussian. And these guys here are actually contributing to the scalar perturbations in the CMB, which on the other hand are observed to be Gaussian, as I said at the beginning of this presentation, to a very high degree of accuracy. So as a consequence, one cannot have a lot of these photons around when CMB scales were leaving the horizon, because we would have also a lot of non-Gaussianities that we don't observe. In particular, this implies that gravitational waves produced at the time where CMB scales were leaving the horizon should be very small if they are sourced by photons, and so their effect is negligible. Is it possible to evade this conclusion and still have observable effects of these gravitational waves in the CMB? The answer is yes, of course. We worked out this model with these collaborators, 10 years ago. The idea is the following. Consider now that the inflaton is phi and is doing its own thing, but there is some other axion sigma that is, on the other hand, rolling only for a few number of e-foldings. And sigma is our axion, so it's the one field coupled to the photons. So now photons are produced only for a bunch of e-foldings. As a consequence, also gravitational waves and scalar fluctuations are produced for a finite number of e-foldings. Now, the strong constraints on non-Gaussianities are valid in the regime in which these non-Gaussian contributions are scale invariant or quasi-scale invariant. But they become very weak when the non-Gaussian contribution is only around a finite number of multiples in the CMB. So if these photons are around only for a few number of e-foldings, this effect can be confined to a finite number of multiples in the CMB, and this can lead to observable effects without violating the constraints from non-Gaussianities. We worked out a few parameter choices for which this happens. These are three choices of parameters. I cannot go in the detail of this, but This, red, green, and blue are different CMB temperature fluctuation lines. These are all compatible with all observations in the scalar fluctuations. You see, you have a peak here at large scales, but then at smaller scales, we don't have any effect coming from the photons. This is for the same choice of parameters. This is the BB correlator. This is what normally should be associated to the amplitude of gravitational waves. So this model can mimic large gravitational waves, well, can actually lead to large gravitational waves only at a certain regime of multiples, which is interesting. More interesting for this conference is parity violation. The B modes that are the polarization modes in the CMB that are sensitive to gravitational waves are parity odd objects. The T modes, the temperature fluctuations, are parity even objects. So in a parity even universe, the correlator BT, average on the whole sky, should give 0. In this model, on the other hand, this is non-zero, and it can be also relatively large, as you can see here, because the system is parity violating. So this is a parity violating signatures that would appear in the whole universe. Let's move on. Let's go back to the simpler case where the axion is actually our inflaton and not a rolling spectator. Now, there's an important consideration also. This constraints of FNL, as I said, apply only to CMB scales. But look again at the power spectra. They go as e to the 4 pi psi, where this parameter psi, as I said, is proportional to phi dot and inversely proportional to h, which means that as inflation progresses, h always decreases, phi dot typically increases, so psi increases. As a consequence, the gravitational waves produced at the end of inflation can be exponentially larger than the gravitational waves that were produced by this mechanism, let's say, when CMB scales left the horizon. So one might have a situation where the constraints from CMB are satisfied, but still one can get large gravitational waves at smaller scales. That is when when gravitational wave interferometers are detecting them. For instance, this is a curve of omega GW as a function of frequency. These frequencies correspond to cosmological scales. So you see now there is no effect. The black line corresponds to no photons, and there's no effects here. But then as you go to larger frequencies, depending on the choices of parameters, one can have curves that might cross LISA sensitivity, LIGO sensitivity. This is an old plot. I will show more up-to-date plot soon. So suppose we have these gravitational waves that are detectable by an interferometer. Can we tell these are chiral gravitational waves? Well, it turns out that if the system is Z2 symmetric, then we cannot tell the chirality. Basically, if we have a planar interferometer, which is the case for a single interferometer, then a left-handed gravitational wave coming from the top is the same as a right-handed gravitational wave coming from the bottom. And if the gravitational wave spectrum is isotropic, these two effects cancel out, and we cannot have a net effect. So planar interferometers are not sensitive to chirality. Of course, the gravitational waves are not isotropic because our Earth is moving with respect to the cosmic rest frame. So one, at least in principle, can have some observability, but turns out that this requires these gravitational waves to be very large. And this is beyond detectability. There are other possibilities of detecting the parity violating nature of the stochastic gravitational waves. For instance, to consider several interferometers. It turns out that LIGO, Virgo, Cagra triplet is not very good because they're all in the northern hemisphere. So they don't violate this Z2 symmetry a lot. We consider the possibility of proposing a gravitational wave detector opposite to one of the LIGO detectors. This should be in Australia. As you see, this is a very ambitious idea, but we had fun considering it at least. Let's move on. Let's go back to inflation. The equation of motion for the inflaton, now the inflaton is coupled to this gauge field, and so the gauge field can backreact to the inflaton. And actually, this strong backreaction regime will happen for large-ish, not so large values of this parameter psi. This is why I said that psi cannot be very large. When psi is of order 5 or 10, usually this quantity here becomes very, very large. In general, this large psi, as I said, happens at the end of inflation. This is where what we are interested in because of various phenomena, including these gravitational waves detectable by interferometers I was mentioning. So it's important we understand it well. It also turns out that this system is a mess. If one assumes that the inflaton is uniform and one solves numerically the system describing inflaton plus photons, and one studies the evolution of parameter psi, one sees that psi evolves kind of a smooth way until, for instance, this point. And here is when strong back reaction kicks in, and now psi starts doing these crazy oscillations. And we have various ways of understanding where these oscillations where they come from, but at the same time, we only have numerical studies to predict how they are really going to go. So one can ask the question, well, psi is doing crazy things, as I shown in this plot, when strong back reaction happens. And though these crazy things reflect in the shape of the left-handed and right-handed spectra? And the answer is yes, of course. So with Juan Garcia-Bellido, Alex Papageorgiou, and Marco Peloso, we studied, for instance, a model of inflation where we have a relatively steep part of the potential that leads to strong back reaction, so large oscillations here. And this is the resulting spectrum of gravitational waves. And we see there's a lot of interesting phenomenology here. The tensor modes, these gravitational waves, have peaks in the spectra. The left-handed and right-handed, the blue and red, are different helicities, are very different. And they might be detectable, for instance, for this choice of parameters, even by PTAs or by LISA. So this looks great. There's a lot of interesting stuff potentially going on. But there's another problem. If one includes inflaton gradients, then the behavior with these crazy oscillations I was mentioning on the parameter psi disappear. The behavior becomes much more smooth. At the same time, this system can only be studied, at least up to now, using lattice studies. And lattice studies, of course, are powerful, but they are not very exhaustive. You cannot cover a lot of parameter space with lattice studies. So we don't have like a general rule of how these things are happening. But what this leads to conclude is that actually we don't really trust this expression that I was showing from this paper from 2023. More recently, Barboni, and Peloso have studied the emergence of important gradients, and they've shown that while, for instance, in the inflaton, important gradients in the inflaton, and what they've shown is that while, for instance, this choice of parameters this spectrum is not trustable, one can cook up other inflationary models where one gets similar spectra with oscillations, and these oscillations we trust because the inflaton gradient stays small all the time. Okay, in the last minute or so, I'm going to discuss two last aspects. One is angular correlations. The gravitational wave interferometers have poor but non-zero angular sensitivity. So one can ask the question whether there can be some angular correlations in the energy between gravitational waves and scalar CMB perturbations. This is work I did with my student Sofia Corbat, and I very strongly encourage you to watch her talk because she's going to talk about this. Another thing, and these are the conclusions, that the correlations can be relatively large. Another thing Sofia did on her own was to study the anisotropies of omega GW. So omega GW of X, omega GW of Y, and she discovered that these models, these anisotropies can be very large, and so they might actually be detectable. last 10 seconds to say that Axion inflation can lead to a lot of parity violating features, and this motivates a lot of search in the data